Hello guys, welcome back to my channel Maison African Motives. Still working on engineering science info. So we are going to focus in this platform actually on statics, where we have got some questions that we need to polish up and manage to work on them so that we can be able to understand how they ask these typical questions. So we have got the first question, which is having a beam, a light horizontal beam, this first part, and also the last part, which is showing us the information, this information where we've got this particular section, and we are asked to calculate the position of the centroid. Okay, we shall talk about that one later on, but as you can see, it's actually 16 marks on statics, which is actually a lot of marks that we have there. All right, so let's see what we have, guys. On the first part, we are given to note the magnitude of A and B are. We are given the magnitude here of A and B, which are the supports. But take note here, this was 25 kilonewton per meter. But if you are to cross check, we are supposed to have it as 25. So you could have worked with 25 kilo. Yes, it's fine, but it was not like giving us the exact thing that we wanted. But yes, it was fine, but the actual value which was supposed to be there was 25 newton per meter if you are working with this question paper. So now from this particular part, the first question is to draw the following: a detailed shear force diagram. That is what we need to draw, the part of a shear force diagram. So how can we have this part? How can we draw the shear force diagram? Okay, this is what you're going to have. Here we have got, remember, we are given the value of A, which is 121,875. This is 875 newton here, and also the value of B here, which is 278,125 newton, like that. Okay, these are the values that we are actually given for now. Now if we are to cross check on our diagram here, let's just find the distance in between here, because we do not have this particular distance, but we know that the whole distance that we have is 12 meters, and from this point to this point is 3 plus 4, which is 7. So definitely 12 minus 7, we are going to obtain 5 meters in this case here. All right, so, and the other thing, let's talk about the distributed load, guys, because here there's a distributed load here. So which means definitely we shall divide it into 2 between 5 meters, which means you are going to be left in between here 2,5 meters, and also in between here 2,5 meters, which is the same thing here. Okay, and also 50 times 5 is going to give us, because we've got 50 newton per meter, so 50 times the distance of 5 meters, which is something like 250 newton. All right, then here we are going to have 25 times 4, which is 100 newtons. So I'm going to show you in a clear way here. I'm just showing you like what it's supposed to look like, and this is going to be 2 meters, and this is going to be 2 meters in between. So this is how you are supposed to like visualize your diagram, guys. This is what I'm just trying to say. You're supposed to visualize it this way. We have got the distributed load between these 5 meters, and we are given 5, which is 50. So we are going to multiply this 50 by the distance of 5. Okay, here we are given 25 newton per meter, so it's 25 times 4, which is 100. Then you separate. Just, you're supposed to have in a mindset of this when you're answering, so that it can be easier for you to have the diagram. Anyways, let's just quickly look at this shear force diagram. I'm just saying, guys, so that you answer properly even the other questions, because it's not about this question, but it's also about the questions which are following. Once your diagram is like that, it's going to be easier for you. So this is 5.11, which is asking us to draw the shear force diagram. So as you know, guys, the shear force diagram, we have to start at 0, and we see what is happening there. All right, so okay, let me just try and increase it again, like that. All right, so let's cross check, guys. First part, we have got at the end, at the left end here, we know that will be at 0, but there's a support which is going upwards. Remember, a support is positive, so it's going to be 0 plus this number, which means definitely you are going to remain with the 121,875 Newton, which is a positive, and this is support, which means it's going upwards in a vertical line. Okay, so you're going to just draw a vertical line. Let's just say here that is where we have got our 121 comma this value for the what, for this support at A, all right, which is 121 comma 875. That is the value that we have. So we are at A. So here we started at 0 Newton there. Then in between these points, let's just say was we are given C and D, so maybe you can just name, okay, this one is A, this one is B, this one is C, this one is D. So this point we do not know it actually, but we want to know what is in between this point and this point. These are the major points. So from A to C, there is a distributed load in between, which we multiplied 5 times that 50 Newton. It was 50 Newton per meter. Then we obtained 250. So we are going to subtract 250 because it's going downwards. It's a distributed, and also you represent with a line like that. So you're going to subtract 250 from this value here. So definitely, guys, if we subtract 250 from 121,875, if we subtract this 250, because it's going to give us a negative, which is negative 128 comma something like that, negative 128,125. This is where our value is now at, but it's where we are representing with a slanted line like that, not a vertical line. So we have to draw up to a negative, and negative, it means it's below this line. All right, so it's going to a negative. Let's just say this is where it is going to be at a negative value here, just below it, below 0. So this is where we are now. We said we are at minus 128,125 here. This is the value that we are having. So this is where we are at this point, which is minus 128,125 Newton. Then what happened between from C to this point B, which is the support here, which is a positive? There is a distance. We are not having any distributed, so which means here we are going to just move a horizontal line to represent that distance. So you just move in a horizontal line, which means you are still at minus 120. You are still at this value here. You are still working with this value because you maintained that line. All right, so now let's see what happened at B. At B, we are having a support which is a positive, so definitely I have to add to this value because a support, it's a positive. So where we are at this value, minus 128,125, if we add this value here at B, which is the 278,125, we are going to obtain 150. Right, that's 150 Newton, if I'm not mistaken there. So you are adding, guys, you add, so it's going to give you 150, and it's going upwards. And also 150 is supposed to be above this one, because yes, it's a sketch, but it's supposed to be meaningful. This is 121, so it's supposed to be above this. And this is a support, just like what we did on this support. It is supposed to go upwards. So you just draw a vertical line going upwards just above this point here. So this is where we are now. We said we are at 150 Newton now. All right, now what happened in between B up to D? There's a distributed load between these points, which is distributed between 4 meters, which we said when we multiplied, it gave us 100 Newton. So we are going to subtract this because it's a distributed load. So we subtract 100, where we are now at 150. So 150 minus 100, we are going to remain at what? At 50. And also that 50 Newton is below this value here. All right, so it's going to be maybe somewhere here. Remember this one, it's a distributed load, so you're supposed to draw a line which is a slanting like that. So this is how it is going to maybe just look like. So we said we are now at 100 minus 150 minus 100, we are now at 50. So this is now at 50 Newton, and also 50, it's a positive. That is why it is above this line. Okay, it's supposed to be above the line because it's a positive. Anything that is below the line is a negative. Positive above the line. All right, so we are at 50 Newton now. Then at D, as we can see, we have got a point load of 50 Newton, which means it carries a negative. So we're going to subtract 50. There is no distance in between. We are still at that same point D. We subtract 50. So now at 50, if we subtract 50, definitely we are going to remain at what? We are going to go at 0 Newton. We'll be at 0 Newton now. So 50 minus 50, that's 0. So this one is going to go down because it's a point load. It goes down in a vertical manner like that. This is what it's going to look like. All right, so we are now at 0 Newton there at the ground. So as we can see, to close like what it is happening, it means we are actually having what the forces which are in equilibrium. So this is positive, negative, positive, just like what we can see on this case, because we said anything above this line, this is the line that is measuring this line. Anything that is above, it's a positive. Anything below, it's a negative. So that's the concept. That's how you just simplify this. All right, so if you have this mindset, it's going to be easier for you to actually draw anything or have anything that you want. Okay, anyways, let's see the other part. The other part on 5.12, the magnitude of the bending moments at, okay, this one is not to do. This question was to draw for this one and to draw for this one. This one is supposed to be calculate. You don't draw bending moment. So this one you're supposed to calculate. All right, no problem. So here we are supposed to calculate the magnitude of the bending moments at the principal points. All right, so there is something that is going to happen here. Okay, let's just talk about the ones which are the major points in this case, because we are referring to the point A, to the point C. These are the points that we are referring: point A, point C, point B, and point D. But if we are to cross check, there is a condition that is going to happen here. All right, when we are having a distributed load, when it is crossing the horizontal axis. So we shall talk about this, where we are going to have another point that is in between, where we are going to have our maximum bending moment. So we just assume we are going to talk about, I'm going to talk about that one. So let's just say it is point X. Okay, I will talk about it later on. So for the meantime, let's calculate the major bending moments that we have, so that we will be able to talk about that one later on. All right, so we have got this is 5.12. so we have got the bending moments definitely at what? At A. That is our first point here, at A. So at A, we have got a support which is going up. We know anything that goes up is a positive. So, but the distance, there's no distance that is moved, which means it's 0 here. So it's going to be 121,875 by 0 there, which is going to give us, remember, force times distance, which is 0 Newton meter, because this was in Newton and the distance in what? In meters. So it will be Newton meter. So that is actually the concept that you are referring to. So this one, we took our bending moments from the what? From the left. Okay, this one was from the left. All right, let's move on, guys, to C. We need the bending moments at C. So at C, what is going to happen? If we are to cross check at C, we have got a distance in between here from A to C, which is a distance of 5 meters. So you're going to multiply, it's a positive, you multiply by 5. Then because of that distributed load, if we are to cross check now, we are going to refer it as 250 now, with a distance of what? Of 2,5 in between. That is when you have your diagram in a simplified manner like this. You simply see that this is 250 and there's a distance of 1,5 and it's a negative okay, because it's a point load. Now we are referring it as a point load because we have already taken the Newton per meter now. All right, so that means we shall have force times distance, this one at A times the distance of what, of 5 meters. So it's 121,875 times a distance of 5 meters minus, because this one is going downwards, it's a point now, so we are going to have 250 times a distance of what, of 2,5 back to C. We are referring to the point C. Force times what, times distance, which is 250 times 1,5. So this one, we took this from what, from the left. All right, so if we are to simplify properly, guys, we are going to obtain a negative, which is negative 15,625. This is what I'm obtaining here, Newton meter. All right, so we took this from the left, so we move on to B. At B, we are now having our support here at B. So taking this, A is now moving back to B, which is now 8 meters, and this 250, because we have got all right, the other thing we are going to subtract is 250 minus 3 plus this 2,5 plus 3. But if you have to cross check, we have got 2 things that you have to consider here. Here we can just consider, okay, still you've got 2 things, but here we've got at least we are not working with these decimals, so we're just working with these whole numbers. So you can even work it from what, from the left. Still you must obtain the same thing from the right, I mean from the right side. So I'm just going to take this one from the right side. All right, so for B, bending moment is going to be minus, because this one is a point load, so it's going to be minus 50 times the distance of what, of 4 meters. So it's minus 50 times 4 minus, again, because this one is a negative as we said, so it's going to be 100 times a distance of what, of 2 meters back to what, back to B. So it's minus 100 times 2. So this is going to give us minus 400 Newton meter. So that is what you're going to have in this case. So guys, as you can see, that it's very, very important that you simplify properly on your calculator there. All right, so let's see another moment, which is at D. But before we do that, let's just see if we could have taken from the left side, because here we took from the right. Okay, this one we took it from the right. Let's say we wanted to take it from the left, it was going to be like this. Like I said, it is going to be from this is going to be 121 times the distance now, which is 8 meters. So you multiply this force times distance, which is now 8, 5 plus 3, this is 5 and this is 3, so it's going to be 8, because you are referring here at B, so it's going to be 8 now. So it will be 121 is a positive also, because they support this one, so it's 121,875 times a distance of 8 meters, this one that you are given. All right, then a negative like usual, but this time is going to be back to B, which is 3 meters here plus this 2,5. So 3 plus 2,5, this one, which is going to give us 5,5. So it will be 250 multiplied by 2,5, we said 5,53 plus 2,5, which is 5,5. So this is 5,5, guys. All right, 5,5. All right, so here we must obtain the same answer, which is minus 400 Newton meter. That is what I'm trying to say. So if you have to cross check, that's how you simply do it. Then at D, we are at the end now. We can simply take it from what, yes, we can take it from, but guys, let's just take it from right direct here, minus 50 times 0, because we are not having any distance which was traveled, which was taken. So we can even put it here, because this one is direct, guys. We can even put it here. Bending moment at D is going to be, we said, minus 50 times 0, which is going to be 0 Newton meter. So that is what we have taken from what, from the right. All right, so guys, if you are to see from these bending moments, like I was saying, these are the ones which are direct from the points which we were given. But there is a point where it crosses the when we see the bending the shear force diagram, when it crosses the x-axis at this point. Okay, I'm going to talk at this point where we are saying that for this one we are going to have our maximum bending moment at that point. So we have to find that value that is going to correspond at a certain point that we do not know for that particular distance. Okay, so this is what is going to happen here. Okay, I'm going to, okay, now let me put my x as my distance. So I'm going to put it this way. Remember, we've got a distributed load here. So we are saying in between, let's just say we've got A, B, all these points up to D. So we are going to just say there's a point E that we do not know where it is actually located for this particular point that we are going to refer. But what we know is that there is already a support one. So we are going to draw a mini sketch for this one. Just a mini sketch for where you want to represent. So we already know that there is a support here because this is just in between that distributed load, so you don't need to draw everything. Okay, we already know that there is a support here at A, which is 121,875. This one we already know that it's given. Also, what we know is that there is a distributed load which is no longer going to be taken as 50 times 5 to give us 250. No, we are going to remain with our 50 Newton per meter. Yes, but the distance has changed. We do not know the distance in between. So we are saying in between here, remember, we had what? A distributed load. So this is what we had already here. We had a distributed load of 50 Newton per meter. All right. Now this is our point we said we are going to have as E. So this is our point E, our new point, which is just in between this point A and C. We do not know where it is actually located, but we know that it's within this region from A to C, as long it is within this region between A and what? Between A and C. That is what is important. All right. Now the distance between these you do not know also. So it is the one that maybe you can refer it as X. So we need the distance between that point because we need to calculate the bending moment at this point E. So definitely we are going to need the distance from the point E to what? To point A. So where are we going to have this distance that we are referring to as X meters? Where are we going to have it? All right, this is the concept. You are just going to use a simpler version to say that since I know that I'm given an upward force here, which is a support, I'm going to take that as an advantage to say that if we are to consider like what we did previously here, I want you to see what you did previously. Previously, we knew that this distance was 5 meters. So we multiplied 250 times 5 to obtain, 50 Newton per meter, this one, times 5 to obtain this 250. It was force times distance to give us this force. Now that means we can know the force that is going to be acting in between this distance of X meters in terms of X. We can actually know that force. Why? Because the distance, we are assuming that distance to be what? To be X. And we are given that we have got a force of 40 Newton per meter. So definitely force per meter times the distance in meters is going to give us the force. So we have got a force of 50 Newton per meter here times a distance which we do not know of X meters. So definitely we are going to repaint with 50 times X, which is 50x Newton. So this distributed load here can be represented as a point load, just like what we did here. But we are doing it in terms of X because we do not know the distance in between and we want to calculate that distance first. So which means this can be represented as 50x in what? In Newton. Now this is what you're going to have. So which means we can clearly see the forces which are going up and the forces which are going down. You can't see it when you are having force per meter. You can't properly see that. But when you put something like this, you can see, okay, this is the force that is going up, so it's equal to this force that is going down. So that is the idea. So F up is equal to F down, just like that. So our F up is this 121,875, which is equal to F down, which is this one that we are now taking. We are now taking it as a normal point load. So it is going to be 50x now in Newton, because it's already in Newton. So how can we find x? Definitely divide by 50 by 50. So x is going to be, so if we divide, we are going to obtain 2,4375, which is in meters. So that is the distance in between these 2 points. Okay, let me maybe write this in another way so that we can clearly see what I'm talking about, guys. Okay, so we say this is going to be 2, or let me use the red one, 2,4375 meters. Okay, so this is the distance that we are having. So definitely we need to calculate what we bending moment, because the distance is now there. And also the other thing, this is our x, so which means we can replace it here to know that our x, because we said this is 50x. Remember, that is what we had. This is 50x, and now our x is there. This is our x, so which means we can actually know this force here. If you want, it's going to be 50 times x, which is 2,4375. Is that so? 4375, yes. So if we multiply this, we are going to obtain, okay, let me just write it here. We are going to obtain 121,875 Newton. Okay, this I'm just showing you. So this force here is going to be 121,875 Newton. That is if you want to write it like that, because now you've got the value of x. And also the other thing, you must know the distance in between these 2 points here, because remember, you need the force and the distance. But this distance is easier because remember, it's distributed in between this distance, so you just divide this by what? By 2. All right, remember, because this will be in between, so you divide by 2, which is going to give you something like 1,21875 meters, which is the same here, 1,21875 meters. Remember, it will be equal for both. So now, guys, our diagram is easier since we want to calculate the bending moment here at E. Therefore, let's calculate it now. So you just take a part of a construction from your diagram. You don't take the whole diagram, just present like this. It's going to be easier for you to see this type of equation. So anyways, bending moment at E is going to be this one is a positive, so you're going to have 121 times the distance x, and we now have the x, which is 2, so it's now easier, guys. 121,875 multiplied by the distance that we took here, 2,4375, the x that we obtained at that time, which is 2,4375. all right, then this one, it's a negative. It's now, you're now taking it as a point load now, because you have separated in between the distance. So remember, we said it's 50x, which gave us this value here. So we are going to use this one now, 121, this one that we obtained when we multiplied 50 times x, which is our distance, and we obtained this value here. So it's going to be minus 121,875 multiply by the distance. The distance also, we said when we divide this x, which is this distance here, by 2, this is the distance that we obtained, 1,218. This is one you're going to multiply, so it's 1, okay, now I'm having space here, so it's 2,1,875. So you're supposed to write up to last, but I'm not having space, so it's this value times 1 comma that value. All right, so that's what you're going to have, and from your calculator this is going to give you 148 comma 5351. It's going to be 5351 and so forth, so it's going to be 535 Newton meter. So that is what you're going to have now as the bending moment at what? At E. So that's what you have, and we have taken this from what? From the left. So just an idea, this idea, guys, if you can visualize this idea, just that idea, this one, if you can just have an idea of this, to say this is actually what is happening, even all these diagrams won't be necessary in future to use them, because you know what exactly you're supposed to do at that point. All right, anyways, that was it, guys, about the bending moments. So we have got our bending moments now. Then what else were we given on this question? We are now given on 5.13 now, which is to draw a detailed bending moment diagram. So using these bending moments, definitely let us sketch, let us draw this. Okay, so I'm just going to show you what is supposed to look like, guys. All right, so this is 5.13. All right, 5.13. All right, so let me just start by drawing my horizontal line here. So definitely the first thing at 0 there, because we started at 0. Okay, these are our bending moments. Remember, at 0 we have a bending moment of 0, then we moved on to C and so forth, but we are just going to take it step by step. All right, if we are to cross check here, we have got the points that are very, very important for us to note. If we are to take this bending moment here from A, which is 0, up to C, you see that we are having a distributed load. Okay, let me show you from the diagram. Okay, this is okay. Here we do not have the A and the value of, okay, we have it from this one. Okay, this was our point C here. As we can see, from A to C, we are having what? A distributed load, which we know that we are going to represent something like that. All right, so but this is going from a 0 going to positive values, because remember, in between A and C we have got bending moment at E, which is a positive. Remember that we have got a bending moment at E, which is a positive, which is actually the maximum value that we have. So which means we are going to a positive, then we go downwards to a negative value. All right, so it is going to be like this, guys. We are going from a positive value to, we are going to a positive value, where maybe this is where we are having our maximum bending moment. Then it goes back to B, which is at what? Is it B or points, which is at negative? But this one, it's a negative. All right, this one, it's a negative at C. So this is at C. So this is at 0 here. This is 0 Newton meter, which is at A. All right, so at this point where we are having a negative here, this is at C, where we are having this minus 15,625 Newton meter. This one is at point C, but we are saying in between A and C, that's where we are having that maximum value that we calculated in between what? In between A and E, and we said let that point be E, and we calculated its bending moment at E, and we obtained a positive 140. That is why you see we are having this. So it's going to be maximum here at 148,535. It was 535, okay, Newton meter. So you just cross check, guys, if the value is actually corresponding also with you. So remember how you represent this. If it is a normal diagram, like when you are not having a distributed load, you represent vice versa, like what you do on a shear force diagram, or you now represent with a slanted line like that, like what you did when you were representing a a distributed load on a shear force diagram. That's how you do on a bending moment for a normal consideration. But when it is distributed, you try to curve like that. Okay, you draw it in a curvy way. But this, because it's going to a positive and also it goes to a negative, that is why it has to be just like that. So I don't know, but you can draw nicer diagrams than me, guys. You know that you can draw actual nice diagrams. So this is at E here. This is our bending moment at E. All right, anyways, we moved on to E, then to C. From C, we have got the bending moment at what? At B, which is minus 400. And this one at B, between C and B, we are not having any distributed here between C and B. This is a straight and normal consideration, which I said you must represent like what you do a distributed load on a shear force diagram. But this is vice versa now on a bending moment diagram. So it is going to be like this up to minus 400. So let's just put it this way. All right, so it is going to slant this time now. So it's minus 400 here, Newton meter. All right, so that's what we have. Then let's move on to another part now between, so this is at what? At B. We are now at B here between C, so this is at B. So we also have the bending moment at what? At D. That is our last part. Bending moment at D, which is 0 Newton. And it's from this B back to, so let me just put my B here down here, guys. So I want to come from this point B up to the last part, which is on this line at 0. But what type of a load was in between? We are having a distributed load in between here. So guys, we are supposed to represent with a set, but it's from this point up to 0 there. So you can just represent with a curvy sec like this. You can just put it in a curvy way like that, just like what you did here from 0 to this point. Okay, but now you're not going to go back again to the 0 because it's going up to what? Up to 0. So it's not going back to the negative. You're just going to take it up to what? Up to 0 here. So we've got our 0 Newton meter, which is at point what? Which is at point D. We say D. Yeah, these are the bending moments at the point D. So that's it, guys. Our point A, our point C, our point D, our point B, and our point D. Then the point E, which is the extra point that you're supposed to note, which you take whenever on your shear force diagram you are going to have a condition where it crosses what? Where it crosses the horizontal line, working with what? With the distributed